Hello, everyone. This is going to be the lecture for section 4.5, derivatives and the shape of a graph. So since chapter 2, chapter 3, right, we've been talking a lot about what the derivative can do for us, right, and how it can describe the description that I've been giving up to now has been the instantaneous rate of change, right, or the slope of the tangent line, right? This section is really going to open up what's called curve sketching. So there's a fair amount of stuff that we can get from a function using its derivatives, okay? So that's what we're going to cover today, okay? Let me go ahead and get into the very first thing. It's going to be a little bit of a review for the derivative for critical points, okay? So it's going to deal with increasing, decreasing critical points, and the culminating bit for this first portion is the first derivative test. Okay, so we know what something looks like if it's increasing, right? We know what something looks like if it's decreasing. We know what a critical point is, right? So let me cover a couple things before we move on. Okay, so the first thing I'm going to cover is this. If a function is increasing, right? Then we know that the first derivative, right, at any point c is going to be positive, right? And likewise, right, we know that a function is decreasing, right, if the first derivative at a value c is going to be less than 0. So what I mean by that, so again, I'm going to go ahead and stick in my x and y, right? I'm going to put two graphs down. Okay, I'm going to do, let's say this one that does this kind of increasing and the other one that does this kind of increasing, right? Hopefully you guys take note, right, that all of these slopes are positive, right? All of them, every single one. And this is for any increasing graph, okay? And then likewise, if we go ahead and do the same sort of thing for decreasing, right? So let's take two types of graphs, right? Whether it's decreasing really sharply like this or decreasing very sort of gently like that, right? And we take a look at the slopes, right? All of these slopes are negative. They are dropping, right? That's what it means for it to be decreasing, right? Okay, so we know that much for now, correct? All right, so now let's go ahead and move on to first derivative test, okay? So let me read it out first because it's gonna look confusing, okay? And I'm gonna fill in these three blanks that are right here. The one, actually two blanks right there, okay? And I'm gonna fill in the little pictures for them on the right-hand side right after, okay? So suppose you have a function that is continuous over an interval I, right? And it contains a critical point C, okay? If f is differentiable over I, except possibly at x equals c, then you have one of three choices, okay? So suppose that your f prime changes sign from positive to negative, okay? So you have a critical value, right? Before the critical value, you are, your first derivative is positive, and then after your critical value, your values are negative, right? Then what we have here is a maximum. You have a maximum at x equals c, okay? And then likewise, this is the second option. Suppose you have f prime and it changes sign from negative to positive. Okay, so before your critical value, it is negative, and then after your critical value, it's positive. Then you have a minimum. Okay. Option 3 says that if it has the same sign either before or after, then you can't make a determination. You have neither a maximum nor a minimum. Okay, what you do have is what's called, you'll learn this in Calc 3 when you get there, you have something called a saddle point. Okay, so the first two choices are the big ones, right? So let me cover how this comes about, okay? And I'm going to do it using the pictures, right? So this one's going to be the maximum, and this one's going to be minimum. Okay, so again, I'm going to go ahead and do an x and a y. Okay, these are your x's and these are your y's, right? I'm going to throw in a graph. So, whoops, wrong graph. This one's the maximum. So, bam. Okay, so we see, right, that that's going to be our maximum point right there, right? We see that that's going to be the critical value, right? Okay, and then here's my x's, here's my y's, and then I'm going to go ahead and go like that, right? So we see that this value right here, I'm actually going to make it an orangey color instead. There we go. That's going to be my value C, right? And this is going to be my value C here, right? Okay. What I want everybody to notice is this, right? So the first one, before my critical value, right, all of these slopes are positive, right? You guys see that? And then afterwards, all of my slopes are negative. Okay? When you have positive slopes before, negative slopes after, you have a maximum. Got it? Okay. And then likewise, right, if you guys take a look at for the minimum, right, these slopes are all negative, right? All of those slopes are downward. And then after the critical value, they are positive. Whoa. Let me do that one a little nicer, huh? There, whoosh. Yeah, that's better. Okay, so if your slopes go from negative before the critical value to positive after the critical value, you have a minimum. Okay, this gives us a pretty good way to find what's called maximums and minimums, and this is the problem-solving strategy. Actually, let me scroll back up. There we go. This is the problem-solving strategy to find maximum and minimum, right? Without using a graphing utility. Okay, so the first step here, right, is find all the critical values, all the critical points of f, and divide the interval into smaller intervals using the critical values. Okay, and I'm going to use the critical values as the endpoints. You'll see what I'm talking about in the example when I do it below. Okay. Step 2, analyze the sign of f prime in each subinterval. Okay. Notice what it says there. Analyze the sign of f prime. You don't need to know the value, just that it is positive or negative. Okay. You'll see what I mean when I get there. Okay. And then afterwards, after you analyze the sign, right, then you can determine the local extremity. Okay. Before your critical value, if it's positive and it goes to negative, right, you have a maximum, or vice versa, then you have a minimum. Okay. You make that determination at the end. Okay. So I think the best way to sort of illustrate how first derivative test works is by doing an example. Okay, so consider this function. Okay, first thing I'm going to do, okay, what I'm going to do is I'm going to just find the critical values for now. Okay, which means I need to take the first derivative. Okay, so I'm going to do it just how I've been doing it in the lectures from before, right? Well, wrong direction. This is going to be my high. This is going to be my low. So my h is going to be x minus 2 squared. My low is going to be x squared minus 2x plus 2. So my high prime is going to be 2x minus 2. My low prime is going to be 2x minus 2. Okay. So here we go. My f prime of x is going to be my low, follow along now, right? X squared minus 2x plus 2 times d high. So 2x minus 2 minus high x minus 2 squared times d low. So it's going to be 2x minus 2 all over the bottom squared. So it's going to be x squared minus 2x plus 2 squared. Okay. Okay, here we go. This is going to have a lot of reduction in it. Okay. If you guys notice, right, both of these have an x minus 2 in there. So what I'm going to do is going to be x minus 2. I'm going to factor in x minus 2 out. And that leaves you, for the first term, it's going to leave you with 2 x squared minus 2x plus 2 minus. Here, I am left with just one of the x minus 2. So it's going to be x minus 2, 2x minus 2. All over the bottom square. All over x squared minus 2x plus 2 squared. Okay? All of this now reduces down to, and I'm going to leave this for you guys to try out. Okay? This all should reduce to x minus 2 times 2x all over x squared minus 2x plus 2 squared. This is f prime of x. Okay? Okay, so now what we were trying to find here is critical values, right? So critical values, right, happen at two spots, when f prime of x is equal to 0, or, right, when f prime of x is equal to a does not exist, or when f prime is undefined, right? So let's go ahead, go through both of them, right? So suppose f prime of x, we'll do the first one first. I'm going to do 1 and 2. Okay, so if I do 1, f prime of x is going to be x minus 2 times 2x divided by x squared minus 2x plus 2 squared. We need this equal to 0. Okay, so now this comes from a handy little fact in math, right? So suppose, I'm going to write this one in pink here, right? Suppose you had an a divided by b, and that's equal to 0. The only way that this can happen is if a is equal to 0. Now, keep that in mind, okay? Some of you guys might be thinking, well, what about the b equal to 0? Keep that in mind. Hold that thought, okay? So in this case, right, if I have a fraction and it's equal to 0, the top's got to be equal to 0. This automatically tells us from here, right, that x minus 2 times 2x has to equal 0. This gives us our two critical values, at least from this one, right? So either x minus 2 has to equal 0, in which case x is equal to 2, or, right, 2x is equal to 0, right? And this gives us the easy one, x equals 0. So our two critical values here are going to be x equal 2 and x equals 0. This is for finding the critical values when the derivative is equal to 0. Now, we still have a second one that we needed to find. So step 2, right, was when we have to do f prime of x is equal to x minus 2. Let me write it down first. All over squared. So the other method for finding critical values, right, is when the first derivative was undefined. So we need to find when the first derivative is undefined, okay? If you take a look at this thing, right, remember this thing that I just wrote down? So if I have a fraction and it's equal to 0, right, then the top's got to be equal to 0. So here's where that thought that I told you to hold on to, right? But if the bottom is equal to 0, then it's undefined, correct? So the way to find this out, we need to find when x squared minus 2x plus 2 is equal to 0, right? And this means, I'm going to do this right here. I'm going to biquadratic equation. You find that x is going to be equal to 2 plus or minus the square root of negative 4 all over 2. Okay. This right here, hopefully you guys remember, right? This is a complex value. This is a complex value, not a real value. So this one produces no critical values. Okay, so that means we only have 2 critical values to worry about, and it's these two up here. The x equal 2 and the x equal 0. That is it. Okay, so now let's move on to the next one. Let's move on to part B. Okay, so part B says use the first derivative test to find all extrema and increasing, decreasing behavior of f of x. Okay, so here is, let me scroll back up to our, there we go, our problem solving strategy. We just did step 1. Okay, we found all critical values, and what we're about to do is we're about to divide our number line into smaller intervals. Okay, and then we're going to do step 2, which is analyzing the sign. Okay, so this is the thing that I want to sort of put a little bit of emphasis on. Okay, so what I'm going to do is this. I'm going to draw a number line. I'm going to whoosh. Yeah. Okay. Actually, I'm going to make it a little bigger. We'll go. There we go. Okay. We know what f prime is. And I like to write it over here just so I know what I'm plugging in, really. Okay. All over x squared minus 2x plus 2 quantity squared. All right. I am going to divide now my number line, right, based on the critical values that I found above. So I'm going to do 0. Actually, I'm going to do 0. I'm going to do 2. Those were our 2 critical values, okay? What we're going to do is we are going to find some test points in these intervals. So one of our intervals is this back here. Let me actually do it in pink. Everything before 0, everything between 0 and 2, and then everything after 2. Okay, those are going to be our 3 intervals. We're going to choose test values within those intervals, and we're going to look at just the sign. Okay, we're going to look at just the sign. So anything before 0 would be a very good test value. What I like to tell everybody is choose test values that really don't make you work too hard for in terms of your mental math, right? So I'm going to choose, this is perfectly fine, right? -1, right? -1 is before 0. That's good. Okay. Next test value I'm going to choose, I need to choose something between 0 and 2. 1 works out pretty good. Okay. And then something before 2, so I'm going to choose 3. Okay. All right, here we go. Like I said, I'm going to be looking at the sign of these test values in f prime. I don't entirely care about the value. I only care about the sign. Okay. Okay, so here we go. So if I plug in, and this is what I'm going to try to, I'm going to write it right here. f prime of -1, okay? I'm going to go ahead and plug it in. Let me grab a highlighter here. -1 minus 2, that's going to be a -3, right? 2 times -1 is going to be a -2, okay? This is going to be 1 plus 2 plus another 2, and that's going to be squared, so it's going to be positive. So it's going to be really what's going to take care of everything is the thing on the top. Hopefully that makes sense for everybody. So it's going to be a -1 minus 2. That's a -3 times a -2. So this is going to be positive. So I'm going to do this, positive. Okay. So we know at least that much for now. Okay. We'll move on. F prime of 1. So I need to plug in 1 into my derivative, which is right there on the left. Okay. So 1 in here is going to be a -1 times 2 times 1. That's going to be 2. So this top is going to be a negative value. Sorry. So I'm going to do this. I'm going to actually negative value divided by, right? If I plug in 1 here, it's going to be 1 minus 2 plus 2. So this is going to be positive, right? So hopefully you guys see that's going to be a positive divided by a negative. So this is going to be negative. Okay. Next one. F prime of 3. So I need to plug in 3 into my derivative. Okay. So if we do that, 3 minus 2, that's a +1, times 2 times 3, that's still positive. So we have a positive up top, divided by, right? Let's look at the bottom. 3 squared, that's going to be 9 minus 6 plus 2, that's still going to be positive, and you're squaring a positive, so it's still positive. So we have a positive thing over here, right? We have it, positive. Let me actually do this thing over here too, just so that it makes sense, right? So we have a positive divided by a positive, right? And that gave us a positive. All right, so we have it. We have everything we need, okay? So at this critical value, so remember, 0 and 2 were our critical values, right? Before 0, the slopes are positive. After 0, the slopes are negative, right? If we use first derivative test, right? This tells us that there's a maximum here, right? Slopes positive before, slopes negative after. That means we have a maximum, okay? And then at 2, right? If we look at the same thing, slopes before are negative, slopes after are positive. This is a minimum. That's it. Okay, so this is how we determine increasing, decreasing behavior and how to find extrema using just the derivative. Okay, so after this comes your first quick check for this section. Make sure you work out every single step. These are, at least I chose, the problems that I chose, hopefully, the derivatives are doable. For the most part, watch your negatives, watch your signs, okay? So yeah, okay. Moving on, I'm going to be presenting a new item in calculus for today. We're going to be studying concavity, the inflection points, and the second derivative test. So hopefully you guys remember what the first derivative did, right? First derivative was the critical values, right? Second derivative is what we're going to be doing this time around. It's going to be called the inflection point, okay? And what that does is it gives us concavity, and likewise, there's a second derivative test to tell us whether or not our function is concaving up or concaving down, okay? So first thing I want to do is define some stuff, okay? So suppose f of x is differentiable over an open interval I, right? If f prime is increasing over I, we say that f prime is concaving up, okay? So remember what f prime does, right? F prime is the slopes of the tangent lines, right? If the slopes of the tangent lines are increasing, we have concave up, okay? And likewise, if f prime, the slopes of the tangent lines, are decreasing over I, we say that f of x is concave down, okay? So, test for concavity tells us, okay, that if f double prime is greater than 0, right, then we have concave up. And if f double prime is less than 0, we have concave down. So this is going to have this definition, or this picture that's going to be on the left here, or on the right, is going to have a fair amount of stuff stuffed into it, okay? So we do concave up here, and then concave down here, okay? So again, I'm going to go ahead and slap down an x and a y, right? Something that is concave up, right? Let me actually draw a, there we go. That looks like it's concave up, right? Is bowl up, essentially, if you guys remember that from pre-calc, right? Okay, and then whoosh, whoosh, x and y, concave down. Okay. Okay, so what I want to cover here is how the first derivative and the second derivative sort of match up, right? So remember what first derivative did, right? It gave you the slopes of the tangent lines, right? Now we're looking at the second derivative. So the rate of change, right, in the rate of change. How quickly are our tangent lines increasing or decreasing? Okay, so what I want to point out is this. So let's go ahead and do concave up first, right? So notice that in a concave up section, right, the slopes before are negative, right? And then the slopes after that minimum or maximum, right, are positive, right? So what we say here, right, as we go that way, right, f prime is increasing as we go that way. Got it? So the slopes in this section of a concave up graph, right, are going from negative values to positive values, right? We say that f prime, the slopes of the tangent lines, are increasing. Okay, same thing, right? If you take a look at the same thing over here, f prime, right, is decreasing. So same analysis, right? So on this side, right, these slopes are all positive, 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 and then they turn negative, right? You guys see that? Cool. Okay. Whenever that happens, right, we have something that's called concave down. Okay, that's how we do the test for concavity. So suppose that we have a function, right, that is twice differentiable over an interval AB. If the second derivative is bigger than 0, right, aka the first derivatives are increasing, then we have something that is concave up. Okay, and if f double prime is less than 0, so the f primes are decreasing, then we have a concave down graph. Okay, this brings me to my next big point. Okay, this idea of an inflection point. Okay, it's when f double prime is equal to 0 or f prime is undefined. Okay, and what this looks like on a graph, right, is when f changes concavity at a point A. So, for example, suppose you had a function, right? And I'm going to do this. I'm going to do like that. And then I'm going to connect it with another one that does this, right? Just so that I can, and I'm going to do this again. So either this direction, and then it changes into, hopefully you guys see what I'm trying to do here. There's this point right here. Okay, you guys see those red sections are concave down, right? And the green sections are concave up, right? Those purple points, both of those purple points are what we call the inflection points. Okay, it's essentially where a function f of x changes its concavity, where it goes from concave up to concave down, or concave down to concave up. Okay, the way you find them using our calculus is by the things that I have right there. F double prime is equal to 0, or F double prime is undefined. Okay? Okay. Which brings me to the second derivative test. Okay? It has 3 options again. Okay? The first 2 are the more important ones. Okay? Suppose C is a critical value of f, and f double prime is continuous over the interval containing C. Okay, then you have 2 options. Okay, so you have a critical value, right? Suppose that f double prime is bigger than 0, then you have a local minimum at C. Okay, if f double prime is less than 0 at C, then you have a local maximum. These look sort of opposite of each other, and they feel opposite from each other, right? Okay, but this is it. Okay, make sure you just whenever you write them down, make sure you write them down in the right order. So if the double prime is bigger than 0, you have a minimum, and if you have a double prime less than 0, you have a maximum. So let me go ahead and draw the picture for it, right? So I'm going to do local max, max, and then local min. Okay, so again, I'm going to draw an x and a y. X and y. This is my x, and this is my y. Okay, so suppose you had a local max. So suppose you had a graph that did, that, right? And then over here, suppose you had a graph that did a local min. So it did whoosh, right? So we know that these points right here are our critical values, right? So this is my point C. This is my other point C. Okay, so notice what happens for all of these, right? Before, the slopes are positive, right? And then after, the slopes are negative, right? You guys see that? So as we go this way, again, I'm going to draw the same picture that I did up above, right? F prime of x, let me just do f prime, is decreasing as we go that way. You guys see that? So we go from positive slopes to negative slopes, right? That means f prime is decreasing, right? This is equivalent to saying f double prime, right, is less than 0. Okay, that gives us our, so this right here gives us number 2, that one. Okay, likewise, for the local min, right, notice what happens before. So before, these slopes are all negative, right? And then afterwards, they're positive. So our slopes are going, let me write it over here, right? F prime increasing. So our slopes, our tangent line slopes, are going from negatives to positives, okay? This is equivalent, as you might guess, right, to F double prime being bigger than 0, okay? That gets us number 1. So I kind of had them in the wrong order in terms of the picture. That's all right. It's there. Okay. Okay, so this is how we find both the second derivative test and the test for concavity is how we determine the direction of the concave up or the concave down for a certain function using the second derivative. Okay, so I'm going to continue on. Whoa, 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 whoa. I didn't want that to happen. Okay, so I'm going to continue on by showing you all how to do the concavity test. Okay, how to determine the concavity for a function just using the second derivative. Okay, so I'm going to continue on from the example that I did, the very first one that I did. Okay, so you guys hopefully recognize this function right here, right? We did its first derivative already. That's this. Okay, I'm going to continue on. I need to find the inflection points. That means I need to find second derivative, set it equal to 0, or find when it's undefined. Okay, here we go. As I've been doing in the previous section, right? I'm going to set that as my high. That's my low. So my h is going to be, I'm going to distribute it out. So it's going to be 2x squared, and you guys will see why in a second. And then my low is going to be x squared minus 2x plus 2 squared. So then my high prime is going to be 4x minus 4. And then my low prime is going to be 2. X squared minus 2x minus 2x. Let me write that x correctly. Plus 2 times 2x plus 2. Whew. All right. Since this is a quotient, since this is a fraction that we're taking a derivative of, I need to use the quotient rule, right? So f, I'm going to start writing it this way now. Double prime of x is going to be low x squared minus 2x plus 2 squared, low d high, so it's going to be times 4x minus 4, minus high 2x squared minus 4x times d low, so it's going to be this one right here, right? 2x squared minus 2x plus 2 times, 2x plus 2, all over the bottom squared. So it's going to be x squared minus 2x plus 2 squared squared. You guys remember from pre-calc, that means you multiply them. So it's going to be to the 4th. Okay, here we go. And I just messed up somewhere. This is supposed to be a minus 2. Aha. And this is supposed to be a minus 2. Hopefully you guys caught that before I did. Okay. Here we go. Okay. As with all of these derivatives, right, when you try to do these by hand, watch your distributions, watch what you're combining, watch everything, okay? It's very easy to overlook that you missed something or that you forgot something or you sort of by accident turned the negative into a positive, just like I did, okay? Okay, so let me go ahead and run this through, yeah? Equal. I'm going to try to combine this, okay? And I'm going to try to show you guys my steps here, okay? So first thing is first, you guys hopefully see that this has an x squared minus 2x plus 2, and this one does too. So I can factor out one of those, okay? So I'm going to do this. X squared minus 2x plus 2, okay? So that's 1. And separately, 4x minus 4 and 2x minus 2, they have the same common factor underneath, right? It's going to be an x minus 1, okay? So what I'm going to do is I'm going to factor out that too, x minus 1. Okay, now I'm going to write down everything that got left behind. So it's going to be big, x squared minus 2x plus 2. I'm going to keep them in the same spots, times 4 here, because that's what got factored out, right? Minus 2x squared minus 4. And both of these got factored out. So that leaves me here with 4. So the 4 came from the 2 up front, and then the 2 that got left behind from this one. All over the bottom to the 4th, right? So x squared minus 2x plus 2 to the 4th. All right. Equal. I'm still reducing here, okay? What we get left with is this. X squared minus 2x plus 2, x minus 1. Okay. If you combine this stuff, the stuff in the blue, you should get something along the lines of minus 4x squared plus 8x plus 8 all over the bottom, right? X squared minus 2x plus 2 to the 4th. Okay, and I'm going to go ahead and finish this up. I get f prime. You draw it nicer, huh? Is equal to, here we go. If you take a look at this right here, it's got a minus 4 I can factor out. Minus 4. The rest of the stuff gets to stay, right? X squared minus 2x plus 2 times x minus 1. And what gets left now is going to be x squared minus 2x minus 2. So notice that it's a minus 2, not plus 2. So we can't cancel that out, but watch what's going to happen right now. So the bottom is still going to be x squared minus 2x plus 2 to the 4th. Now, remember when I factored out one of these up front, right? So at the very beginning, this one cancels one of these. So our final f prime, sorry, f double prime, is going to be equal to, actually let me write it, no, let me write it down here. Minus 4, whoa, let me make it a little smaller, huh? Minus 4, x minus 1, x squared minus 2x minus 2 all over x squared minus 2x plus 2 cubed. We are done. We found our second derivative, and I think I do have enough space. Let me see. I'm going to grab this. What a time to be alive. I'm gonna throw it over here. There we go. Running off the page a little bit, but that's all right. And it forgot a parentheses. There we go. Okay. We have our second derivative. Now, we need to find the inflection points, right? So that's when, so let me write them here. Inflection points, right, is when f double prime of x is equal to 0, or, right, f double prime of x is equal to does not exist. Okay, we're going to use the same thing that we did with our first derivative test, right? So we have a fraction, so f prime double prime of x, we know we have it, minus 4x minus 1, x squared minus 2x minus 2 all over x squared minus 2x plus 2 cubed. I need this equal to 0. Okay, we know how this worked out before, right? If we have a fraction equal to 0, the top's got to be equal to 0. That's the only way we can get it equal to 0. So that means x minus 1 has to equal 0, or x squared minus 2x minus 2 has to equal 0. This one gives us our easy one. X has got to be equal to 1. The second one, we need to use quadratic equation. And that gets us x is equal to 2 plus or minus, I'm going to write it out, and then I'll give you the decimal values, all over 2. The two values that you get are negative 0.732 and 2.732. We have our three in this case, inflection points. So this means that our function may change concavity 3 times. Okay? Okay. We do the other one now. So remember, right? Just like, let me do it over here. I'm going to put 1 here. Hopefully the numbers or the coloring makes sense here. Number 1, right? Step 1 was first derivative or second derivative equal to 0. We got our 3 points there, right? The next one, 2, tells us that we need when the second derivative does not exist, right? So we need f double prime is equal to minus 4x minus 1, x squared minus 2x minus 2 over x squared minus 2x plus 2 cubed. So we need this thing right here, the second derivative, to be undefined or does not exist, correct? So we already did that work though. So this thing, if you guys remember when we did first derivative, right? X squared minus 2x plus 2, right, does not produce, let me put it, does not real values. Okay. U-E-S, there we go. It does not produce real values. Okay. So what we have here then, right, is only 3 inflection points that we need to worry about are these 3 down here. Okay. Okay. So now, let me recenter this. Come on, there we go. Let me scroll down to part B, using the second derivative test or the test for concavity to determine the concavity of f of x. Okay, so now we're going to determine whether our function is concave up or concave down and over what sections. Okay, and we're going to do the exact same thing that we did with the I'm going to do the exact same thing that we did with the critical values, right? But in this case, we're going to use these inflection values, these inflection points. Okay, so I'm going to do the same thing. I'm going to do a number line. Okay, I'm going to do f double prime because I really care about f double prime this time, right? What was f double prime? There we go. Minus 4 x minus 1 x squared minus 2x minus 2 all over x squared minus 2x plus 2 cubed. Okay, here we go. So our inflection points give us sort of our intervals that we need to be caring about, right? So I'm going to do -1 right here, or +1, right here. I'm going to do 2.732 there, and then I'm going to do the -1 over here, -0.732 over here. Okay. Again, just how we did with the critical values, right? I'm going to be choosing test points. Okay, and I only care about the sign for those test points inside of f double prime. I'll move that down a little bit so it's not. There we go. Uh-oh, not what I wanted to do. There we go. Okay, so again, choose test values that don't work your brain too much. So negative 0.732, a good test value, maybe -1, right? Between negative 0.732 and +1, 0. This one's going to be a little bit more like 2, right? And then after that, I'm going to choose a test value of 3. Okay, all right, so let's go. F double prime of -1. Okay, like I said, I only care about the sign. Okay, I only care about the sign of -1 when we plug it into f double prime. So we throw it in here. So -1 squared is going to be 1 plus 2 minus 2. So it's going to be 1, right? That's going to be a minus 2. So -4 times a -2 times a plus. So it's going to be a positive up top. Okay. And then the bottom is going to be, so -1 squared is going to be 1. Plus 2 plus 2. So it's going to be 1 plus 2 plus 2. And then we're going to cube it. So this is going to still be positive. Hopefully you guys see what's happening here, right? We have a positive second derivative. Okay, let's move on. I'll cover the concavity after we do the rest of them. So f double prime of x, f double prime of 0. This one's going to be a little simpler. 0 minus 1, that's going to be a minus, right? 0 squared, 0. 0, negative. So it's going to be a -4 times a -1. So it's going to be a positive times a -2. So it's going to be negative. So it's going to be negative on top divided by 0, 0 plus 2 cubed. It's going to be positive. Hopefully you guys see this is now equal to negative. Okay. F, whoops, wrong color. f double prime of 2. 2 minus 1, that's going to be positive. 2 squared, that's 4. Minus 2, oh, sorry, minus 4. So it's going to be 4 minus 4, 0 minus 2. So it's going to be so this is going to be a minus 2. Let me get my signs right. See, this is what I'm talking about. That's going to be 4 minus 4 minus 6. So it's going to be a minus 2 times 1 times negative 4. So that's going to be positive divided by 2 squared minus 2 times 2. So it's going to be a 0 plus 2. So it's going to be positive. Cubed, right? Positive. Okay, and hopefully maybe you guys already see this. F, whoops, wrong color. F double prime of 3. 3 minus 1 is going to be 2. 3 squared, 9, minus 6, minus 2. That's going to be positive, right? Positive times the negative 4 out front, so that's going to be negative divided by 9 minus 6 plus 2. That's still going to be positive, so positive here, negative. Okay. So we have our second derivative for our test values, okay? All that's left is to determine whether you have concave up or concave down, okay? And that's back to the second derivative test at this point, right? So since these slopes are positive, right? This tells us you have concave up. These slopes are negative, right? Concave down. Concave up, concave down. There we are. We have the concavity for our function, right? We have the concavity for our function based off of the second derivative test. That's it. All right, so now there's one thing left for me to do. And what that's going to be is the second thing, the very last thing I'm going to have to do here is I'm going to use the result from the first derivative test and the second derivative test and the test for concavity, basically what I did for the two examples, to provide a rough sketch, okay? And how I'm going to do that is this. I'm going to go ahead and grab this right here. Okay, I'm going to copy it. I'm going to paste it down here. Come on. There. I'm going to paste it right there. I'm going to drag it over here. I'm going to put that actually down below. I'm going to scroll back up to first derivative test and grab my table for that one. I'm going to grab all of this, copy it, we'll put that down here. There we are. Okay, so let me actually grab, sorry you guys. Hopefully you guys didn't see that. Hopefully it didn't screw up too much. I'm gonna grab this and move it over a little bit. Just right there we go. All right. So I want everybody to take a look at this, and I'm gonna go ahead and zoom out so we can have, oh, come on. So we can have our tables and our graph at the same time. There we go. Okay, so this is first derivative test, right? this is second derivative test and the test for concavity, right? Okay, so what I'm going to start doing now is I'm going to start sketching this thing, okay, based solely off of what we have here, okay? Now, I'm not going to make a big deal about exact points. This is supposed to be a rough sketch, okay? But if we want to find those points, we can grab these values and throw them back into the original function. It'll tell us exactly what we need, okay? All right, so, so the first thing I'm going to do is this. I'm going to do the first derivative test first, okay? I'm going to grab my blue. I have critical values at 0 and 2 from first derivative test. I know at 0 I have my max, and at 2 I have my min. So I'm going to do this. I'm just going to go ahead and slap down some points. I'm going to do one right there, and then one right there. So at 0, I have a max, and at 2, I have a min. Okay. Now I'll move on to second derivative test, okay? Up to negative 0.732, I'm going to go ahead and actually draw those points in. Negative 0.732 looks like about right here, maybe, right? Next one is at 1. And the next one after that is 2.732. So that's going to be about maybe like one right here. Okay. These 3 points are going to be my changes in concavity. Okay. Everything before negative 0.732 is going to be concave up. So I'm going to go ahead and do this. I'm going to, like I said, it's going to be it's a sketch, right? It's supposed to be just a sketch. So up to right here, it's concave up. And I gave it a nice little concave up there, right? Okay. Between negative 0.732 and 1, it's supposed to be concave down. So I'm going to do, there we go. Okay. Between 1 and 2.732, it's supposed to be concave up. Notice how the graph is already sort of telling us what to do, right? Whoa. There we go. And then everything after 2.732 should be concave down. So I'm going to go ahead and whoosh. There we go. And let's do it a little more. Okay. So our graph should look something like this. Our graph should look something like this. Okay. And lo and behold, right? I've already graphed it for everybody. Okay. Now, let me put both of them side by side. Is it exact? Heck no. Like I said, I'm not too worried about exact points. I do expect everybody to interpret everything correctly, okay? Second derivative is positive, you know it's concave up. Second derivative is negative, concave down, all that good stuff, okay? My graph is not too far off, you know, barring the is exactness, right? Of the points, which, like I said, if we wanted to find the actual values of these points, the maximums and minimums and the inflection points, I can grab those values and throw them back into f of x, and they give me the actual values that I need, right? But like I said, I'm only looking for a rough sketch. Only looking for a rough sketch, okay? So yeah, there we go. This is how we find functions. This is how we're able to graph functions solely using first and second derivative. Okay, cool stuff, right? Okay, I believe, second quick check, I'm making you guys do the rest of your first example. Okay, so continue on and go ahead and provide me a rough sketch. Okay. I would highly suggest, I hope everybody does this just for, the sake of learning calculus correctly. Try to do these, both the first and second quick checks. Try to do them without using a graphing calculator. You're more than welcome to use it afterwards. I want you to put down an answer first, okay? Then double check your work, okay? Yeah, okay. Try these out, and I think that is it. I think it moves on to lecture questions after that. Yep, that's it. If there's any questions, I have my office hours. Make sure to check my availability in my semesterly schedule that I provide in the Canvas page. Besides that, happy studying. Hope to see you guys around.